last lecture, after looking at, essentially we started to think about how we have, so far have seen spin angular momentum operators, nuclear spin angular momentum operators, orbital angular momentum operators, all these different types of angular momentum in our quantum systems. We introduced this sort of idea of a generalized momentum that we basically use if we don't, if we're not concerned with what the source of or what type of angular momentum we're talking about, we can sort of identify, well, it's an angular momentum, it's going to have these general properties, and there's going to be operators that relate to it. And essentially, for all of these types, we know that each of those has two quantum numbers associated with it. It's sort of angular momentum quantum number, and then the magnetic quantum number, or that Z component quantum number. So in general, there's going to be some J squared, where J is just that general momentum, and it's going to have an eigenvalue equation where if it's operating on an eigenket defined by that angular momentum quantum number and that magnetic quantum number, it has an eigenvalue h bar j plus 1 operating on that jmj eigenket. There's going to be a Z component operator that has the eigenvalue equation on the same eigenket that has eigenvalue mj h bar jmj. And this, like all of these operators or angular momenta, had these same sort of properties here. We also introduced, and for all of these things, if you choose some j, some angular momentum quantum number, that sort of defines what we call the manifold of mj states, which can be equal to, they go from negative j all the way up to positive j in integer steps, right, or the possible values. And this defines some manifold, or you can think of it as a ladder of eigenstates. After looking at this, we then defined these, what we call ladder operators, the raising and lowering operators for angular momentum that are analogous to our ladder operators in the harmonic oscillator. These are defined as the x component plus or minus I times the y component of that angular momentum, and the action of these action of these ladder operators on one of these eigenkets is to essentially go up or down through this manifold of m sub j states, right? So what we had was j plus or minus operating on j mj. It was equal to h bar times the square root of j plus 1 minus mj plus or minus 1. And what it does is it takes this eigenket, and shifts it to 1 up or down in that manifold of mj states. So we sort of developed all of these tools, or these angular momentum type operators, and how we can think about just general angular momentum. And we did this because we were looking at the hyperfine interaction, that interaction between the angular momentum of the proton, or the nucleus in hydrogen, and the electron in hydrogen. And that hyperfine interaction, after a lot of work a few videos ago, we showed, in the cases we're going to be discussing, is equal to a constant we sorted out, h bar squared s dotted I. So we have two of those angular momentum operators that we just discussed, one associated with the electron spin and one associated with the nuclear spin. And we have to figure out how this Hamiltonian perturbs our hydrogen atom and causes energy shifts in that. So in general, we're going to be using these types of angular momentum operators to sort through this. And that's what we're going to do today. We're going to build, take those angular momentum operators we introduced last video, and sort out the perturbation or the energy shifts due to this hyperfine interaction Hamiltonian. To figure out how this Hamiltonian affects our system, we're going to, in perturbation theory, a lot of what we have to do is essentially figuring out the matrix elements of these perturbation Hamiltonians, right? So we're going to have to sort out this Hamiltonian in matrix notation. The problem is to represent an operator in a matrix, in matrix representations, we need to have a basis that representation is in, right? So let's think back to this hyperfine Hamiltonian and remember where it actually came from, right? We had this large, this dipole interaction among between the angular momentum of the proton and the electron, and we ended up reducing it. A lot of the terms ended up being zero for what we were looking at, and we had this hyperfine interaction. Hamiltonian was, it had a bunch of constant terms outside that ended up relating to our this A constant here. We ended up eventually sucking them all into one constant, but it looked something like this: A over h bar squared, 8 pi over 3. And it was that S dotted with I, the delta function for R. And what we had to do is we realized that this Hamiltonian operated on two different spaces, right? We had this sort of spin space here and then the position space here of the wave function. And we had to figure out, how this operated on our ket, and our state ket had to have sort of a space part and a spin part. And what we did was just sort of realize that we had the spin part of our ket and the space part of our ket there. So our whole ket had to sort of introduce both. And we mentioned the formal way of doing this was the tensor products in that, but we were able to just sort of, since these were separable, take the space part and the spin part and have them just have this operate on the space part, and these two were going to operate on the spin part, right? And that's what we dealt with. But now that we did that, and this, if you remember the space part operating on this, it was just, this ended up being just the magnitude of the wave function at the origin, because that's what the delta function is. We figured it out. It gave us a constant, and we plugged it all in, added it all to this, and that became our A, and we were left with just this spin part. But we're faced with sort of a similar challenge here, right? Our Hamiltonian is basically proportional to the electron spin operator dotted with the nuclear spin operator, right? That's what our hyperfine Hamiltonian is proportional to. And this, if you think about it, operates on two different spaces, right? We know that the electron spin has a two-dimensional space that it operates on that's spanned by that spin up and spin down bases. Or if we were to write it in terms of our generalized sort of momentum quantum numbers, those eigenstates are the S is equal to 1/2 and the M sub S is equal to plus or minus 1/2, right? So we have sort of an electron spin space, right? And we have, the same sort of thing for the proton, where we have a nuclear spin subspace, or if we write that this way, it would be I equal to 1/2 for a single proton, and M sub I is equal to plus or minus 1/2 for that spin up. This Hamiltonian is going to act on both of those, and we have to figure out, well, what makes the basis states, right? The electron spin's two-dimensional basis, the nuclear spin's two-dimensional space. We have a Hamiltonian that's acting on both. And again, the way we're going to have to figure this out is the proper, more formal way of doing this is sorting out tensor products and all that in general, but you can kind of just hand-wavy see how this is going to go by considering the fact that the kets that we're going to have to make up are going to somehow have to include both of these things. There's going to be we'll say a plus state for the electron and a plus state for the proton that's going to sort of include both of those things, right? And so what it ends up being is it's going to have an S quantum number an I quantum number, an M sub s quantum number, and an M sub I, quantum number. And it ends up being a four-dimensional space. So we had, these two spin up and spin down basis states that we could use to describe our spin subspace for the electron, and similarly a proton spin up, proton spin down to describe the subspace for the proton spin. We can make a basis that describes the combined, the space that includes both of those spins by sort of taking the tensor product between those two spaces, but it's going to be a four-dimensional space that includes essentially every combination of these basis states, right? So the set of basis states that describes the Hilbert space that includes both the electron and the proton spin is going to be defined by those four basis states that are the S, I, M sub I, M sub S states, where S is 1/2, so S is going to be 1/2 because the electron's a spin 1/2 particle. I is going to be 1/2 because the proton's a spin 1/2 particle. Mi can be plus or minus 1/2, and M sub S can be plus or minus 1/2, and that's that. So we sort of define a new basis that this operator can operate on. If we wanted to, rather than writing out all four of these quantum numbers, the only thing that's really changing is whether the proton or electron are spin up or spin down. We can sort of make it simpler on our lives notation-wise and take this S, I, M sub S, M sub I, that list of quantum numbers, and let's just, for an example, 1/2, 1/2, we'll do 1/2 and 1/2. Just when they're both spin up, we could just write that as spin up, where, we'd have to be clear, the first spin up is referring to, say, the electron, the second spin up is referring to the proton or the nucleus, but we can write all our four basis states could be written, like that in our familiar way. And we've sort of defined the basis that spans the subspace that this Hamiltonian is operating on. Once we have that, now we can do, if we use that, if we've defined a basis, we can take a generalized state a generalized spin state that includes both the spin of the electron and spin of the proton, and we can write it as a linear combination of those basis states, right? Something like this. Beta, let's go with gamma next. And because it's easier for me to draw, I'll use eta for that last one. But now that we've defined our bases, we're going to call this, and we'll get to why in a bit, the uncoupled bases. I can now write this in a matrix notation as just that column vector of those coefficients, right? Just like we did for all our matrix representations before, all we had to do is sort of define the bases we were using for that matrix representation. And when we have this, we can now figure out the matrix representation for this just by knowing how it behaves on our basis vectors, right? Because in this matrix, in this basis, in this matrix representation, we know that Hamiltonian is going to have a matrix representation H11, H12, H13, H14, H21, ... It's going to have a matrix representation like that all the way down to H44, because this is a four-dimensional space, with Hij being the those matrix elements are defined this way, where I and J are, this is the first, the second, the third, and the fourth bases states in our thing. So if we know how that Hamiltonian operates on these for basis vectors, we can figure it out in that matrix representation. We'll have our perturbation Hamiltonian in a matrix representation. We can then, do our perturbation theory with it, sort out what the energy shifts are and the corrections to that. So, for example, right, we have, an S squared operator, or let's look at the SZ operator. So this is the electron spin and Z component operator operating on some state. We want to know how this operates. Well, it's the electron spin operator. It only operates on the electron spin part of our wave function. So if we look at, plus plus, and again, the order matters here. This is the Z, the spin up for the electron. This is the spin for the nuclear spin. This operating on that's going to give us the plus h bar over 2, or times plus plus, or written kind of in terms of these quantum numbers, this gives us ms h bar plus plus. And if this was operating on the minus plus term, this is going to be equal to, again, ms h bar minus plus, or just negative h bar over 2 for this electron thing, minus plus. And we do the same thing for the plus minus and the minus basis states, and we've figured out the action of that operator on all our basis states, so we can use that to map to our matrix representation, right? They're all going to have this h bar over 2 on them because it's a spin 1/2 system, and if we write our matrix elements, it ends up being 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative 1, 0, 0, 0, 0, negative 1. These uncoupled basis states are eigenvectors of our SC operator because, think about how we define them. We define them with the eigenvalues or the quantum numbers associated with those Z operators. So it's expected to be diagonal here. And, again, in terms of our basis vectors that we're writing this matrix representation in, these are the rows and the columns for that matrix representation. Similarly, the S squared operator, we can do the same sort of thing there, and this ends up being here. Let me give a bit more room here. This is just going to be 3 h bar squared over 4, sorry, that's a little small there, times the identity, because again, it's diagonal. These states were sort of defined by these basis states were sort of defined by the eigenvalues and eigenvectors of these operators. And you can do the same thing if we look at the Z component of the nuclear spin operator. We get this h bar over 2. This ends up being 1, negative 1, 1, negative 1 across the diagonal, and zeros everywhere else. And you can see that, right? Because again, we're in this plus plus, plus minus, minus plus sort of bases, and this I operator operates only on the nuclear spin, which is positive, minus, on those things. The I squared operator in that representation is, it's just the same as this one, right? Because it's got the same eigenvalue for all of them. But we can set up these sorts of matrix representations just knowing how these operators act on our basis states. And in the uncoupled bases, we sort of set up those basis vectors as, using the eigenvectors of those operators. So everything's all well and good. Now our Hamiltonian involves S dot I, which is just going to be take the dot product of those Sx Ix plus Sy Iy plus Sz Iz, right? And we've sorted these out here. Our basis states are eigenvectors for those operators, so we're fine with that. But the z components and the x and y components don't commute for these z operators. So these are going to have different operators. We're going to have to sort out the action on our basis vector with those. But we can sort of be clever about this. And in the last video, we defined those raising and lowering operators, those general j plus or minus as jx plus or minus I jy. So in this case, for the s operator, there's going to be an s plus or minus raising operator that we can use as the sx plus or minus I sy. And if we use these definitions, we can write these sx and si operators sx, ix, sy, iy operators in terms of these ladder operators for the s and the I for the electron and nuclear spins. And then when we do that, we know how these raising operators operate on our basis kets, right? Because all they're going to do is take our z component eigenvalues that are defined, those manifolds, and go up or down the ladder of states that are allowed for those values. So the idea is we can, convert this operator into an operator. We can write it in terms of s sub z components and our ladder operators, and then we're sort of set up. We can have it in matrix representation because we know how all of those things act on the basis, the uncoupled basis that we're sort of writing our Hamiltonian in. Now it's a pretty straightforward sort of derivation, converting these x plus y, and I'm going to give it to you all as a homework assignment. But when all is said and done, this sx ix plus sy iy, part of our Hamiltonian, can be written as 1/2 s plus I minus plus s minus I plus, right? And again, we know the action of all of these operators on our basis vectors, so we can write this in matrix representation, right? So all in all, if we take this part and replace it or write it in terms of that, and then the other part of our Hamiltonian is the s sub z, I sub z operators, we have our Hamiltonian, our hyperfine interaction perturbation can be, it was a over h bar squared s dot I, can be written as a over h bar squared. That s dot I is just this, which we can replace that part with there. So this hyperfine perturbation is 1/2 s plus I plus minus rather plus s minus I plus s sub z I z. And that's we've now written our Hamiltonian in terms of operators that we know how they act on our basis vectors, which is all we need to know to write this operator in matrix notation. To essentially do that, right? We have to remember our ladder, our termination conditions, sort of thing. Like we have essentially s plus acting on plus plus equals 0, right? There's no state higher in the manifold than that spin up state of the electron, so that goes to 0, just like s minus operating on that minus plus state equals 0, and vice versa. So if we remember those, the way those act on there, we can just literally take this Hamiltonian and operate on each one of these basis vectors to get what our matrix representation is. And when all's said and done, after you do that, figure out all those terms, that s dot I part of our Hamiltonian in matrix representation is h bar squared over 4 times, we have 1, 0, 0, 0, 0, negative 1, 2, 0, 0, 2, negative 1, 0, 0, 0, 0, 1. So, and you can see, there is a non-diagonal part of this matrix, but we now have our, multiply this by that A over H bar squared over 2, and we have our Hamilton, our perturbation Hamiltonian in our matrix representation. So let's step back and remember where we are, all right? So we were looking at, we had the Hamiltonian of our system we had written as H naught plus our perturbation Hamiltonian due to the hyperfine interaction. So this was just our Coulomb interaction. This was our simple H atom Hamiltonian, and the hyperfine interaction was our perturbation Hamiltonian. And we focused on the hydrogen state, that n equals 1 ground state, right? Which in our hydrogen atom, we had ignored spin degrees of freedom and all that. But now that we're including these electron and nuclear spins, we see that this is actually a degenerate state in when we consider that, spin up or spin down on those electrons, that 0th order Hamiltonian has the same states, so those are degenerate. When we included that, what we've done now is sort of define this Hamiltonian in that degenerate subspace that's spanned by those 4 uncoupled basis states, right? And now degenerate, so we're going to apply degenerate perturbation theory to our perturbation Hamiltonian, and degenerate perturbation theory essentially says diagonalize the perturbation Hamiltonian in the degenerate subspace to find our perturbed states and eigenenergies, right? And we've essentially just written, we've left out the H bar squared, or the A over H bar squared part, but we have our perturbation Hamiltonian in the degenerate subspace there. So our task is now to diagonalize this Hamiltonian. A convenient thing we have is that, there's only a submatrix that's not already diagonal, right? So we can already see sort of that the plus state that corresponds to that row and the minus state that corresponds to that row, those eigenstates are still eigenstates after after including that perturbation Hamiltonian. So if we take, if we want this to actually be our hyperfine, wanted that to be black. If we take this and our hyperfine Hamiltonian was just A over H bar squared times S dot I. So this H bar squared becomes an A, and because the H bar squared is canceled. This is our perturbation. We know that the sort of first energy eigenstate is going to be our plus basis state. Our other eigenstate, we'll call it, the second energy one, is the minus state, and they have, E1 has an energy shift of A over 4, and E2 has a shift of A over 4 as well, right? Because those are the eigenvalues of this perturbation Hamiltonian. So I guess these are the first order shifts. Should probably include that. So now we're tasked with sort of diagonalizing this non-diagonal submatrix here to figure out what the third and fourth states, eigenstates end up being, and what those eigenenergies are. To do that, we know how to diagonalize these submatrices, right? We take our characteristic equation, which is essentially, and I wish I had more room. We're looking at the determinant of that submatrix. So the negative A over 4 minus our eigenvalue. We have A over 2. We have A over 2. and negative a over 4 minus our eigenvalue. So the determinant of that set to 0, solve for lambda, we have our energy shifts. If we do that, if we take that determinant, this is quite simply just negative a over 4 minus lambda squared minus a over 2 squared, which has the solutions, right? You take the square root and you have essentially negative a over 4 minus lambda is equal to plus or minus a over 2. And the results of this are lambda is equal to a over 4 or negative 3 over 4 a are the two eigenvalues when we diagonalize this non-diagonal submatrix here. So doing, when all said and done, we now know that our third and fourth energy eigenvalue perturbations are going to be another shift. One of those states shifts the same a over 4 that these two first states did, then the other one drops 3 over 4 times that a in energy. To figure out what states these actually are, what the eigenstates are, we just use, we take essentially the eigenvalue equation where we have a over 4, that the matrix we're looking at, which was negative 1 to negative 1, operating on, a, if we're doing this one, we'll call it a sub 3 and b sub 3, is going to be equal to that energy, which is a over 4, a sub 3, b sub 3. So this is essentially, the subspace, that Hamiltonian subspace time operating on that E3 eigenstate is going to be equal to that energy times that E3 subspace. So in matrix form, it looks like this. We get the equations negative A3 plus 2B is equal to A, which essentially gives us that A is equal to B. Normalize that, and we realize that that E3 vector in our matrix representation is just 1 over root 2, 1, 1, right? The A's being equal, and then normalize it. This matrix representation is in the subspace that we're looking at, right? So that's in terms of the plus minus and the minus plus basis states. So our third, our perturbed energy eigenstate is 1 over root 2 times plus minus plus minus plus. And that's the first one. We do the same thing for the other eigenvalue, and what we end up with is the same sort of thing. It's just plus minus 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 plus. So what we've done here now is we figured out the 4 shifted, I'll just rewrite them all down here. After including the perturbation and applying our degenerate perturbation theory, we have the following perturbed states of our, the 1, 0, 0 unperturbed hydrogen energy functions, the spin states of the perturbed, this is our unperturbed energy eigenfunction for the hydrogen atom, including the spin degrees of freedom, and applying that perturbation. The spin parts of these state functions after the perturbation are plus plus, E2 is minus minus, E3 is equal to 1 over root 2 plus minus 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 plus, sorry, and E4 is 1 over root 2 the same thing, but minus in there. Right? They have perturbed the energy shifts. Are these three all shift upwards by a over 4. This one shifts downwards 3 over 4a, right? These actually end up getting the name, these three states, because the three states all shifted together and stuck together. These are the triplet states, because there's a triplet of states there. And this is our singlet state. And that's where we're at. So in terms of energy levels, if we just wanted to plot energy here, we have the 100 unperturbed hydrogen energy level here, so that negative 13.6 eV. After the perturbation, we have some energy shift up by a over 4, and we have the other term, the other state shifts downwards by 3 over 4a, and these are the triplet states, the plus plus, the minus minus, what I would call the polarized triplets. All their spins have the same z component, and then the plus minus plus minus plus, what I would call the unpolarized triplet, and then at the bottom here we have the singlet state, plus minus 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 plus. And that's what the hyperfine interaction does and how it changes, how it affects our hydrogen atom. This total energy shift between the sets of states that have been split up, this delta E has been measured extremely well. It's essentially just equal to A, our constant there, but it is 5.88 times 10 to the minus 6 electron volts. And if you remember, the energy scale that we're set with is 13.6 eV is 1 Rydberg for the n equals 1 state. That's sort of our energy level. So this is about 1 million or so times smaller than that, hence the name hyperfine. It is several, orders of magnitude smaller than the energy scale we're looking at. The book has some interesting discussion about how the wavelength for that sort of radiation is about 21 centimeters, and since hydrogen makes up most of the matter you can observe in the universe, they use this transition to sort of map out the distribution of matter in the galaxies and all that. Look at the book for more detail on that. It's not really my area of expertise, but it is pretty interesting. And that's that. So we've looked at the hyperfine interaction. We've done quite a bit here. We'll discuss a lot more in our synchronous sessions, but basically using these generalized momentum operators and we defining sort of a larger spin subspace for our hyperfine Hamiltonian, we were able to use degenerate perturbation theory and apply and diagonalize our perturbation Hamiltonian and sort out these the energy shifts and that due to that hyperfine interaction. What we're going to look at next is something that we could have simplified our lives a lot, right? We used what we called the uncoupled bases. These four states as our basis vectors to write all of our Hamiltonian and all our matrix operators, or all our operators in matrix representation. We used these uncoupled basis states. We could have, if we had some sort of insight or knew that it would make our lives easier, used these sort of coupled states, what we're going to call a coupled bases, as our basis vectors to write this Hamiltonian, our perturbation Hamiltonian in. And in that state, our Hamiltonian's already diagonal, so we could have got all of these energy shifts just by inspection, really. We could have saved ourselves a lot of effort, but we
would have had to know ahead of time what basis is sort of the good basis to use for this Hamiltonian. And in the next video, we're going to discuss the uncoupled versus the coupled bases and what makes sort of a good bases. And we'll get to that. If you have questions, definitely bring them up in the synchronous sessions or email me. We'll discuss this a lot more. I will see you then.